Have you ever really thought about what makes a curve smooth versus what makes it, jagged and sharp? Well, in this explainer, we are going to crack the code on one of the biggest ideas in calculus, differentiability. So if you're gearing up for your CBSE or NDA exams, you're going to want to stick around. We're going to make sure you absolutely nail this.
Okay, let's start with something fun. Think about a roller coaster. What's the difference between a ride that's thrillingly smooth and one that's just dangerously pointy? That feeling, that difference between a gentle curve and a sharp, sudden corner, well, that's pretty much the key to understanding this whole concept.
So, as you might guess, in math, this whole idea of smoothness has a proper name. We call it differentiability. Let's really dig into what that actually means.
Right. So, a function is differentiable at a point if its graph is just perfectly smooth right there. And by smooth, I mean no gaps, no breaks, and absolutely no sharp corners. It's this smoothness that lets us zoom in like infinitely close and find one single exact slope, a tangent line, at that very spot.
Okay, so how do we check for these pointy bits with actual math? We don't just eyeball it, right? No, we use a really specific, two-sided test that puts the curve under a microscope. We call it the LHD versus RHD test. Now imagine two tiny people walking along the curve toward the exact same point, but from opposite sides. The person coming from the left measures the slope right up until they get there. That's the left-hand derivative. And the person from the right does the same thing. That's the right-hand derivative. For the curve to be truly smooth, they have to come up with the exact same number for the slope. They have to agree.
And here's the classic example you'll always see, the absolute value of x, right at 0. Think about it. If you approach that sharp point from the left side, the slope is always -1. But if you come at it from the right side, the slope is +1. They don't match, not even close.
And this right here, this is the golden rule. If you remember one thing, let it be this. A function is differentiable at a point only if the left-hand derivative equals the right-hand derivative. And of course, that value has to be a real, finite number, not infinity.
So this brings up a super important connection. If a function is differentiable, meaning it's smooth, then it has to be continuous. I mean, you can't find a slope if there's a big hole in the graph, right? But, and this is the catch, the reverse is not true. A function can be perfectly continuous, like our good old absolute value of x, and still have a sharp point where it fails the differentiability test.
All right, let's get practical. It's time to build your toolkit. These are the go-to formulas and rules that you absolutely need to have in your back pocket for your exam.
These guys right here, this is your bread and butter. The power rule, the derivatives for sine and cosine, e to the x, and natural log. You just gotta know these cold. It's the non-negotiable first step to solving pretty much anything.
So what happens when you have two functions multiplied together, like x squared times sine of x? Well, you can't just differentiate each part separately. That's where the product rule saves the day. It's a simple pattern. Derivative of the first times the second, plus the first times the derivative of the second.
And you guessed it. For functions that are divided, we have the quotient rule. Yeah, it looks a little more messy, but trust me, it's just another pattern. Once you practice it a few times, it'll stick.
Now, listen up. This quote here says it all. The chain rule is the MVP. It's the one you're going to see over and over. And why? Because so many things in the world are functions inside of other functions. It's how you deal with that complexity. It's like taking the derivative of an onion, layer by layer, from the outside in. Okay, now that we have the basics, let's level up. We're going to look at some pro-level techniques. Think of these as your secret weapons for those really tricky questions designed to trip you up. So you see a problem that looks just awful, like a function raised to the power of another function, something crazy like x to the power of sine x. Your secret weapon here is logarithmic differentiation. You take the natural log of both sides, and that lets you use those handy log properties to bring the exponent down and make the whole thing manageable. It's a lifesaver.
All right, what about those equations where x and y are all mixed together and you just can't get y by itself? You know, like the equation for a circle. For these, we use a technique called implicit differentiation. You basically just differentiate every single term, and the only trick is, whenever you differentiate a y term, you just tack on a dy by dx at the end.
And finally, our third pro move is for parametric equations. This is when both x and y are described in terms of some other variable, usually t for time. To find the slope, dy over dx, it's actually pretty simple. You just find the derivative of y with respect to t, and then divide that by the derivative of x with respect to t. Easy. And now for the best part, the payoff. Let's see how this toolkit we've just built completely demolishes some actual exam questions. Let's do this.
Okay, here's a classic one-mark question. You've got y equals sine of x squared. How would you even start this? Well, you should immediately see that it's a function inside of another function.
And that's our cue for the chain rule. The outer function is sine, the inner is x squared. So you differentiate the outside part first. The derivative of sine is cosine, so you get cosine of x squared. Then you multiply by the derivative of the inside part, which is 2x, and boom, you're done. The answer is 2x times cosine of x squared.
All right, question number 2. This one brings us full circle, right back to our very first idea. Is the absolute value of x minus 3 differentiable at the point x equals 3? In other words, is there a sharp, pointy corner at that spot?
Well, let's run our smoothness test. The left-hand derivative as we get closer and closer to 3 is -1, but the right-hand derivative is +1. Since -1 does not equal +1, they don't match. Case closed. The function is not differentiable at x equals 3.
And that brings us to a super crucial exam tip, straight from the source material. Seriously, don't take shortcuts on this. When a question asks you to test for differentiability at a point, you have to always check both the left-hand and the right-hand derivative. Never just assume.
So there you have it. You've got the core concepts, the essential formulas, and even the pro-level techniques for differentiality. And look, this is way more than just passing an exam. This is about understanding the fundamental language of change. So the question is, now that you have the tools, what change are you going to measure first?